Bismillahirrahmanirrahim. Assalamu alaikum. Consider this dynamical system now. X prime to be ax, where a has complex eigenvalues. Say alpha plus iota beta and alpha minus iota beta. Okay? And what we want to do, we want to convert the system x prime to be ax into y prime to be by such that b is in canonical form. Okay, so we are basically converting matrix A with eigenvalues complex into canonical form. First thing that we want to discuss is this. Consider this only this eigenvalue alpha plus I beta. Like this is sufficient to consider this and work out with this. At the end of the day, we can conclude that this is fine to work with only one eigenvalue. Okay, so if this is complex, then eigenvector must also be complex, naturally v1 plus I v2. Like it could be of this form, maybe v2 can get the form 0 0. So we claim that v1 and v2 are linearly independent, and we want to prove this, that for this eigenvalue alpha plus iota beta, this eigenvector of this form v1 plus I v2 has nice property that v1 and v2 are linearly independent, and we can prove that v1 and v2 are in fact linearly independent. And what are these v1 plus I v2? This is an eigenvector corresponding to this eigenvalue. So here starts the proof. So we want to prove that v1 and v2 are linearly independent. Suppose not. In other words, suppose that v1 and v2 are not linearly independent. So that means v1 is multiple of v2, or v2 is multiple of v1, same thing. Now I know that av is equal to a times v1 plus I v2, but this v1 is c times v2, c times v2 plus I v2. So this is equal to c plus I times a v2. Similarly, because this v is eigenvector for this eigenvalue, so av can also be written as lambda times v, but lambda is nothing but alpha plus iota beta times v plus iv, v1 plus I v2. But this v1 is equal to c times v2, so this is nothing but alpha plus iota beta times c v2 plus I v2. Okay, and which can be written as alpha plus I beta times c plus I times v2. Now if I label this equation as 1 and this equation is 2, then this is also av equal to this, and this is also av equal to this. So I can compare this v1 and equation 1 and equation 2, and at the end of the day I get c plus I times av2 is alpha plus iota beta times c plus I times v2, and this guy gets cancelled with this, so av2 is equal to alpha plus I v t times beta times v2. Now you notice that this left side is real because v2 is real and matrix is real, entries are real, so this multiplication must be real. But this is involving iota, in other words this is complex. In other words, this part is purely real and this part is not purely real. Like, other words, the other part is complex or involving imaginary. So that's basically the contradiction. And this is why we say that v1 and v2 are linearly independent vectors. So if these two are linearly independent vectors, then I can define T in this form, v1 v2. Okay, don't forget that v1 and v2 are vectors which are in this form. For v1 and v2 are the eigenvectors obtained from this v1 and v2 are the vectors linearly independent obtained from this eigenvector, which was for this eigenvalue alpha plus iota beta. So you will first find this eigenvalue, and for that you will find eigenvector, and then you have these two parts, and from these two parts you are making this matrix T. And we have already shown in the previous parts that if you apply this T on E1, then it is V1, and if you apply it on to E2, it's V2. Next thing that we want to see interestingly is, let's consider this AV, which is equal to alpha plus iota beta times V1 plus V2 iota V2. This can further be simplified as V1 plus iota V2. This is equal to alpha V1 plus iota times alpha V2 plus beta times V1 iota minus beta V2. Okay, so this is AV1 plus iota AV2 equal to alpha V1 minus beta V2 plus iota common alpha V2 plus beta V1. Okay, and from here I can conclude that AV1 is equal to this real part is equal to this, and this is alpha V1 minus beta V2, and this imaginary part is equal to this part, so this is AV2 must be equal to beta V1 minus alpha V2, sorry, plus alpha V2. So we need to keep these things in head. Okay, so like we have these things in head. T operating onto E1 is V1, T operating onto E2 is V2, and from here you can also have E1 equal to T inverse times V1 and E2 to be T inverse times V2. We also have AV1 equal to alpha V1 minus beta V2, and AV2 is equal to beta V1 plus alpha V2. Now let's see what form this T inverse AT, what matrix form we want to see this matrix B equal to this assumes. So we know that for finding matrix form we need to apply it onto the basis. So let's apply B onto E1. This is equal to T inverse ATE1, which is equal to T inverse AV1, which is equal to T inverse AV1 is equal to this alpha V1 minus beta V2, which gives me alpha T inverse V1 minus beta T inverse E2, which is alpha times E1 minus beta times E2. Okay, so like this matrix, when we apply this particular transformation, when we apply on E1, we get this result, and when we apply this transformation on E2, let's see what we get. So this is T inverse A T E2, which is equal to T inverse A V2, because this T E2 is V2, and then A V2 is equal to beta V1 plus alpha V2. Then you can operate this T inverse and you will get beta times E1 plus alpha times E2. So what we have at the end of the day, we have this. We have T inverse AT operated onto E1. This gives me alpha E1 minus beta E2. And then when I operate T inverse AT onto E2, other standard basis, I get beta E1 plus alpha E2. And then from linear algebra we know that the matrix of T inverse AT should look like alpha and minus beta will form the first column, and then beta and alpha will make the other column. So this is now in the canonical form. Okay, so in this way you can convert the non-canonical form system into system where matrix assumes canonical form. So what we did, let's summarize it. So we are given with the system x prime equal to ax, and luckily a has, if you get complex eigenvalues, okay, right? In other words, a has complex eigenvalues. Okay, so when a has complex eigenvalues, so there will be two eigenvalues. Either you will be having alpha plus I beta or alpha minus I beta. So you just will pick one of these, okay, and you will call it lambda 1, maybe alpha plus I beta, and then you will calculate corresponding eigenvector, which will be v equal to some real vector v1 plus iota times some other real vector v2. Now from these, like, you don't need to touch this other eigenvalue, you just pick one eigenvalue, you calculate eigenvector, and then from these v1 and v2 you just need to form this v1 v2, this matrix, and then you calculate its inverse, and then T inverse AT becomes the matrix such that this system will be converted into, in this form, T inverse AT, where this system has canonical form. In other words, this matrix will have canonical form, and which will be easy to recognize whether it is a spiral sink, spiral source, or purely imaginary. Thank you.